So now we're going to take a look at some work with the method of annihilators. And in particular, we're going to be looking at still going to have our homogeneous part have constant coefficients. For this most part, that's what we're going to be working with. But what we now have is we have a non-homogeneous differential equation. So like say, for example, we have something along these lines. D squared plus 2d minus 3y is equal to 2e to the 2x. So unlike in previous times where we had this equal to 0, where that part was equal to 0, it's now non-zero. And so we have some slightly different ways of dealing with this. What we want to know is that, or what we want to get is that we're going to separate out our solution into two different parts. We're going to have the complementary part, YC, right, which is the solution to the homogeneous part of the DE. And then we'll have YP, which is a particular solution to the non-homogeneous differential equation, to the DE, just the DE in general, okay? All right, so the first thing that we need to do is to find the solution to the homogeneous part. Now, this is going to be, so we have d squared plus 2d minus 3y. We're going to set that equal to 0 to find our homogeneous part. So we've done this several times before. P of r, our auxiliary polynomial, is going to equal r squared plus 2r minus 3. And so then we set that equal to 0. R squared plus 2r minus 3 equals 0. And so this gives me r minus 1 times r plus 3 equals 0. Okay? And that gives me that r equals 1 and r equals negative 3. Okay? Awesome. That's it. Step one. All right, so now my general solution, my complementary part, my YC, is going to equal C1 e to the x plus C2 e to the negative 3x. Okay? And what I'm going to do is I'm not exactly going to set that aside, but we're not going to use that so much to do the non-homogeneous part, at least in this case. Now, what I need to do is I need to go in and I'm going to see, I'm going to look at that non-homogeneous part. So my f of x is equal to 2e to the 2x. Now notice that's e to the 2x, right? So that's different from e to the negative 3x and e to the x, okay? So those are linearly independent, right? Those three solutions or those three functions are linearly independent. You can use the Wronskian in order to kind of check that. And the reason why that's so important is because that's going to affect what we use as our as our annihilator or as our trial solution. And I'm going to use trial solutions for this one. So what I'm going to notice is that since these three are different, I can simply use yp equal to a, or a naught e to the 2x as my trial solution. Because whatever I end up with for a naught, right, okay, I'm still going to end up with something different than, or linearly independent from e to the x and e to the negative 3x, all right, which is exactly what I want, right? So you notice, right, that 2x is different from x and negative 3x, and so consequently, I'm going to use this. This is going to be my trial solution, okay? There's my trial solution, all right? Now, once I have my trial solution, what I'm going to do is I'm going to substitute it back in and then solve. So that's going to be d squared plus 2d minus 3 times a naught e to the 2x equals 2e to the 2x, right? So what's going to end up being really cool is that we're really, like, you know, at the end of this, when we actually get all of our calculation done, we're going to end up being able to get rid of the e to the 2x and just end up with an a naught and some constants and just solve for that a naught. Okay, so let's do this. So we've got a naught e to the 2x double prime plus 2 times a naught e to the 2x prime minus 3 a naught e to the 2x. Okay, and this is then going to equal 4 a naught e to the 2x plus 2 times 2 a naught e to the 2x minus 3 a naught e to the 2x, which equals This is 4. This is 8 minus 3. That's 5. 5 a naught e to the 2x. And that is equal to 2 e to the 2x. So we've got 5 a naught e to the 2x will then equal 2 e to the 2x. Okay. And so consequently, we get 5 a naught equals 2. And that then gives me a naught equals 2 over 5. Great. What that means then is I can go back and substitute that into y of p. So yp is then going to equal 2/5 e to the 2x. Ta-da! Now, all I got to do just to finish this up is I'm going to find. I know that y equals yc plus yp. So that's c1 e to the x plus c2 e to the negative 3x plus 2/5 e to the 2x. And notice x, negative 3x, and 2x, they're all linearly independent. That's exactly what we need, right, in order to be able to generate the entirety of the solution. All right, and there it is. So 1, solve the homogeneous part of the differential equation. 2, determine the trial solution by comparing the non-homogeneous yc to f of x. Okay. 3, substitute in the trial solution once you figured it out. Into the dE. Okay. And solve for the constants. 4, combine yc and yp. Okay. And that's it. All right.